Okay, can you see my presentation moment?
Yes, Aras. You have to switch. If you
Okay.
go display and then switch the yeah, yes, and then presentation mode. Yeah, perfect.
Okay, thank you, Arya and Oliver, for inviting me for this webinar. So today I want to talk about our activities in DTU energy and how we use modeling for our research. And the topic is multi-scale, multi-physics modeling approach for optimizing P2X systems. So the topics that I want to talk is first some introduction, motivation, and then different levels of the modeling that we have in DTU energy. So the first question is why modeling? Why we kind of need modeling? So first of all, it's faster than the experiments. So we can, for example, simulate 5 years of the lifetime of the stack in 1 minute. We can get further insights from it, for example, by EIS modeling that I will talk later. It's much cheaper than experiments, especially in industrial level, and for stack and system, it's much more expensive to do the experiments. It's not easy to measure some of the parameters. You can try different scenarios before testing them, and also this kind of technologies is a multi-scale phenomena. So we have different scales, and we can try modeling in different scales and get knowledge from the each scale. So the first level is electrode level that we want to try to use our modeling to understand some kind of a phenomena. For example, the targeting here is to understanding the nickel migration, degradation in solid oxide cells. We also want to limit the parameters because in the real cell we have 2 electrodes, we have electrolyte, and we have different initiators of the degradation. So by this kind of testing and modeling, we can limit our problem to very narrow part and only in the fuel electrode. So in here, we want to see how can we model and how we can understand the nickel migration, and is there any way to limit that, mitigate this kind of degradation? So to do this, we have this setup, and we also use modeling to understand how it going on. And so in here, you can see the defect concentration and the charge flux, and we do believe that in the SOEC mode we have these oxygen vacancies that increases the ASR resistance, and by changing the SOEC mode to the SOFC mode, we can reduce it. And there is a company that patented this idea, and we want to understand why this is happening. So the next level is the cell level that we can have detailed multi-physics modeling. We have some test facilities in DTU. We can build a very detailed model of this setup and use it for understanding the temperature distribution, the electrochemical performance, and also distribution of the species in their very realistic physics-based model, and try different things. But this one is time-consuming, and sometimes it's not suitable for our aim. So we also have other modeling, such as advanced EIS modeling. So we have EIS measurements for the SOECs. We can use our modeling to understand the degradation during the lifetime. We can propose some novel methods to reduction of the degradation, which I will talk about it in the system level. We can also use this kind of modeling measurement to check the health of the cell during the lifetime of the stack. So in here, you can see one cell of the SOEC. You can see the measured response of the cell that we have measured in DTU. We also try to model this response during the lifetime of the 1,000-hour test that we have done. By this kind of modeling, we can analyze the coupled process, gas transport, and electron chemistry. We can deconvolute the gas conversion part and diffusion impedance on this degradation. We also can, as you can see, predict the impedance evolution over lifetime of the SOEC due to degradation. So yeah, we also have this measurement that without using any fitting and based on the physics-based model, we can predict the lifetime and also the degradation under different operating conditions by using modeling and the prediction of this degradation. So the next level is the stack level. And we want to see, is stack modeling more challenging than the cell? And the answer is yes. So in stack level, we have, beside the cell, we have different metallic and sealing layers. So in this picture, as you can see, we have this green layer, which is the cell. And beside that, we have several layers of the like foams, like interconnects, contact layers, and considering all of these in the model, it's a bit challenging. So beside the cell test, we need to have some thermal stress analyzers. We need to do some thermal management because it's not in a controlled kind of volume as a cell test. We need to have the correct flow distribution because if we don't have uniform distribution, then the degradation will increase. We also have some possible variation in the height of the stack because of this manifolding. We also have this scale and computational time problem because we have different layers, and if we want to solve each layer, so it will be very time consuming. In here, you can see also one example of the stack from Julish and the detailed model that is published in the literature. So what we use modeling for stack, we can use detailed design for the stack design. In here, you can see one of the DTU designs that we have here. We use modeling for ensuring of the uniform gas distribution to checking and testing the electrochemical performance, to check the pressure drops, to design the manifold, and also for thermal management. Here you can see some of the results, for example, the species distribution, pressure drop, and also the IV curves for different conditions. We can also use some more detailed analyzes like stress analyzers. We have glass sealing in the stack because we want to seal different parts to mitigate and remove the gas leakage because it will kill the stack. So we want to keep the stresses in a standard level. We can also have some crack analyzes in the ceilings by phase field modeling. In some of the conditions, we have harsh conditions and our ceilings may crack, and we want to see what are the vulnerable regions for this kind of cracks. We can also do some creep analysis. So we want to study after a few years of the operation how the creep will be in some component of the stack. But how computationally expensive is this kind of detailed stack modeling? Here are a few examples of detailed models in the literature. As you can see, for one single simulation, it can vary from 20 hours to 40 hours to just try one single operation condition. So it's quite time consuming. So how we can tackle this problem, this time consuming and computational time? So we developed a homogenization approach in DTU. As you can see here, this interconnect and other parts are very, have detailed geometry. If we want to have computational meshes in all of them, it will be very time consuming. There was some partial homogenization idea in literature to kind of homogenize the gas part and then have the detailed part for the interconnect for the cell. And we take one step beyond that and we use the homogenization method for all of the stack, for all of the layers that we have. And with this method, we can reduce the computational mesh and time considerably. So how efficient and accurate is this approach? This approach is used for different commercial stacks. As you can see in here, we have tried it with different SOSC commercial stacks with Elcogen from Finland, Salidera from Italy, and also Sunfire from Germany. We consider all of the involving physics. It's 100 times faster than the detailed model. We can simulate turbulence, we can simulate the stresses, we can simulate the degradation or the lifetime of the stack, and we can also be couple it with the detailed model for local calculation. So what does it mean? For example, for having the thermal stresses in a specific region of the stack, in a cell or in an interconnect, we can get the temperature from the homogenized model, we can get the thermal stresses, and then by some localized sub-models, we can find out is a stack or the cell layer can handle that kind of stress or no. So we can also get some local information by sub-modeling and using this kind of model. So the next question is the system level, and we want to transfer all of our learnings from previous levels to system level to see how we can operate this system to have the lower degradation. So we know that SOSCs degrade over time. We can operate it with constant volume, which we call potentiostatic. We can run it with the constant current density, then the voltage will increase, which we call it galvanostatic. And there's another new way to operate these kind of systems to kind of increase temperature, inlet temperature, to compensate this degradation, to have both voltage and current density. And so we need some heating for doing that, we can get from downstream processes. So how to assess the efficiency of the system? We developed a model in DTU energy by quasi-2D cell simulation with combined pinch analyzers to see how this kind of operation modes affect the performance and efficiency. So in here, you can see some of the results. The galvanostatic operation can reduce the electrical heating, as you can see in here, but increase the stack consumption, and then it reduces the efficiency. While potentiostatic reduces the stack consumption with constant electric heating. But because the voltage, the current changed, the outlet hydrogen production will be reduced. So regarding the efficiency, you can see the potential galvanostatic can maintain the efficiency during the stack lifetime. So this is the way to go, kind of, and most of the companies using this approach now. So the last part is the economic modeling of this kind of system. How we can have more realistic economic analysis. So first part is that we should consider different steels for cold and hot operation part, because we know that the cost of the steels for BOP, for balance of plant, is different. We should consider degradation effect. We should also consider the scale effect. As our colleague from Stisen mentioned, by scaling the production, the cost reduces tremendously. So we consider all of these factors, and we have a modular design for the cold part and also for the hot part, which is we consider higher than 400 Celsius. In here, you can see also the cost breakdown for different operation modes. And as you can see here, the the most important part is the electricity price, and this is important because this kind of electrolyzer has the highest efficiency, and because the electricity cost has the main part in the cost of the hydrogen, so higher efficiency of the SOEC is an advantage for it. And in here you can see some cost breakdown, some future cost breakdown. For example, if we can use some heat integration, some optimized heat exchanger sizing, some stack cost reduction, and other things, we can reduce down the cost of the hydrogen, hopefully in future, to €1 per kilogram. It's very ambitious, and some of them maybe are not that realistic, but with having this kind of assumption, for example, electricity price of 40, 30, 20, and 10, we can obtain this kind of cost in the future. So I will finish my presentation with this slide. We also have other activities that we use modeling for Power-to-X, for example, ammonia production system, methanol production system, conventional alkaline multi-scale modeling, supercritical alkaline design. And for X2 power, we also have ammonia fueled SOFC, methanol fueled SOFC, and high temperature system. And yeah, at the end, I want to thank for your attention.
Thank you, Arash, very much. Maybe we should move on to the next speaker, Mr. Santosh Gurunath. Santosh, are you in? Then you can probably think of sharing your screen. That works. Fantastic.
I hope you can hear me fine.
Yes.